Why PVA? So that's what I want to answer in this video. All right. And the simple answer is I want to know what F is, right? And if you think about F equals ma, well, it's kind of obvious I needed the A of PV and A because that stands for acceleration. But it really depends on the system that you're applying this to. But certainly, it's more often than not you're going to need P and B. All right. And so with the mass spring damper, we unpack F equals ma. And we get this, right? That this is pretty much the same equation, m times the second order derivative of x with regard to t, that's the same thing as a, all right? So right-hand side still m times a. And so unpacking F, well, we see that there are really three components. It's a mass spring damper. Now, the thing I'm really interested in understanding is how much force do I need to apply to this mass to make it move the way I need to, all right? And that's one component of what this total F is. It's being felt by that mass, and that's what I'm labeling here as F of t. But of course, there's the spring force, minus kx, and the damping force, minus b times dx dt. All right? And so if I do this little rearrangement, we'll see this in this kind of classic ordinary differential equation form. It's second order with constant coefficients, and it has a driving function, F of t. Okay, but really all I really care about is F of t. And it's this idea that I kind of know what I want to happen. I know how I want to move that mass. Well, that's what we do as engineers all the time. And very specifically, we do this by developing controls that will make things happen. All right. And so the point I want to really get across now is this may look like an ordinary differential equation, but this is an algebraic equation because we're going to make x be what we want it to be, and therefore x of t is known, and hence dx dt is known, and the second order derivative. And with that thought in mind, maybe that's why it kind of makes sense that we return back to kind of not calling it things that look like derivatives, and we replace it with, well, I kind of rearranged it a little bit, but there's your second order derivative a, then your first b, and then there's your x, which we're going to call p. So p, B, and A. All right, so let's try this out on a mass spring damper, and see what it looks like. All right, so I built this little mechanical model. I'll hit the run button. All right. Okay, and for a mass that weighs 1 kilogram and a spring damper with a K equal to 100 and a damping constant equal to 2. Notice the units are Newton meters and Newton whatever seconds per meter. All right, that this is the response you would get. Right, and this is what you'd call a pretty classic underdamped system. And very iconically, we kind of attach it to what we expect for a mass spring damper, an oscillation that gets kind of decayed or damped down. Right. And we saw that from SimWise in the previous video that we can rapidly get it into Simulink by exporting to this XML format. All right, so let's get to the MATLAB side now. All right, and we're in the directory right there, and there's our XML file. With a body named mass. And mass has a mass equal to 1, and the units implied are kilograms. There we are. And we have a spring damper with the parameters here that we're just highlighting. Most notably the spring constant of 100 and damping constant of 2. And down just a little bit further, we have the actuator right there. And it's through that actuator that we apply the force. All right, so let's bring it in, put the directory in where my app is, and let's launch the app. All right, so very simple interface. Select the XML file, go to the directory, select mass spring damper, and we'll watch it auto-generate the Simulink model for us. Okay, there it is. All right, let's just kind of move it a little bit like that. Let's hit space bar. Let's get a constant in there. And that will be the driving force, which I believe was equal to 5 in the SimWiz. We'll measure from the actuator. It's actually what we call a bus signal. And so the export creates a measurement on the actuator, provides motion, force, velocity, and power. Select motion. Motions could be one of these PVA things, so we need to unpack that. And a PVA is going to be 3 scalar signals, position, velocity, and acceleration. And so we get that. And let's put a scope on position, and let's hit run. All right, and so that's, I think, pretty close to what I can assure you it's the same thing we had on the SimWiz side. All right, so what I want to do now, though, is kind of get kind of old school Simulink, and I want to kind of, really see the equations and how it gets solved by, kind of professional tools like Simulink. All right, and so from my Simulink browser, I'm going to go to commonly used blocks. I love commonly used blocks. I use these quite frequently. And I'm going to pull out a subsystem, and this could be our mass spring damper. We're going to go inside in a minute, but before we get to that, I want to just kind of set it up with, the key parameters, which we know to be the mass, the spring constant, and the damping coefficient. All right, and you do this with these kind of tools here. And so I'm going to drag in and edit, and I'll name this first one mass, and I'll put in units of kilograms. And we're going to have a parameter called m, which is going to be the assigned value for the mass. So I'm going to do the same thing for spring constant and damping. Okay, so you'll see I set up the assignment for the spring constant K and the damping constant B. Let's hit save. Let's go into the block, all right, and put in the values that we originated inside SimWiz. 100 for spring constant, 2 for damping constant. All right, and we're going to compare between the two. All right, and I'm going to just compare directly in that same scope. All right, obviously these will not be the same because we've done nothing at this point to construct our mathematical model of the mass spring damper. And just for your information, the default for a subsystem is send it straight through. Whatever your input is, that will be your output too. All right, but let's go in there and let's just go to work. Oh, actually, before we do this, I want to name this. All right, and I'm going to name it MSD for mass spring damper. All right, and because this is masked, I hit that little arrow to get inside there. All right, and first thing I do is I want to set up the interface. Force will be my input. And position, which I'm going to call X, will be my output. And now I want to formulate the mathematics that we were looking at earlier with the ordinary differential equation for a mass spring damper. All right. And commonly used blocks, I want to get an integrator and a gain. All right. And certainly a big part of getting to position is to, I'm going to label the signal P, but basically P and X are the same thing, is to kind of line up this really important chain, 2 integrations of acceleration to get to position. Right? And so the intermediate signal will be B, and this will be your A, but it's called force right now. And so we got a little bit of work to kind of get to the force, especially the force is going to be carried by the mass. Right? And all right, and so F equals ma, therefore A is equal to F divided by M. So we'll multiply that F by 1 over M. All right, and it knows what M is because it's attached to the subsystem through that mask we created, right? And so here's kind of where it becomes a mass spring damper, which is, well, we got to apply the force that's actually felt by the mass, and that force is going to have some dependency on both velocity and position, right? And so we get an add block in there. Okay. All right, and so so we're going to set it up so that basically we can accommodate both the damping and spring force. And so I'm going to set up with imports being 2 minus, so it's going to be minus plus minus. I'm going to put the minuses on the outside and the plus on the inside to receive our applied force, right? And that spring force, of course, is based on position, and it needs a proportionality constant, which we happen to call K. Right? There's K right there. Right? That's basically multiplying it by 100, and then we'll do the same thing to get the damping. Okay, so that looks pretty good. Basically, the blue curve's on top of the yellow curve, which means that my SimScape multi-body version and then my equations-based approach validate quite well. Right. And to really kind of get to the point of this video, we're going to do this next part, right? And space bar, give myself a little bit of room. And this time, I like that we have that mask in there, but we got to change the name a little bit. So I'm going to call it MSD inverse, right? Inverse is like a word, mechanical, especially mechanical dynamics, people really like. And it's basically, instead of sending force in and getting position, we're going to do it the other way around. We're going to send position or motion in, and we're going to get the force out, right? And we're going to use this to achieve a trajectory we want. All right, so we'll kind of get there in a moment, but let me kind of get started by going back in here. All right, and you know, first of all, we're not going to do calculus anymore, so we're going to get rid of these integrators. And I kind of like keeping all this stuff, but we got to do some redecorating. All right, and it'll begin with my input port. I'm going to name this, you know, motion is now our input. You know, have this little designation of PVA, indicating it to be the position, velocity, and acceleration. What's our word for it? Scalar signals being kind of brought in together, and therefore we'll unpack this with the demux block. And I'm going to make it the same size as this guy. So I'll go to Format. I like this a lot. Match the size. Set this up. All right, and let's put the third port on. So I just click on kind of the edge there. And yeah, I kind of talked about it. I think I might have talked about it earlier, that this is about algebra now. All right, and so we're going to send this in here, and basically we're going to add up these three signals. All right, and then the three signals are the spring force, which is, you know, kx, or position times this value k. The damping, which will be velocity times that damping coefficient v. And then the last one, of course, will be m times a. If I only had like 5 seconds to make the point, this is where I would make it. That's why you want position, velocity, and acceleration. All right? And with that, this will now be the force. And that's the driving force I'm looking for that will achieve the motion that we're going to send in right there. So that looks pretty good. And now I'll go to my browser. I'll say my second favorite catalog after what we call it, commonly used blocks is Terry's Electrical and Mechanical Components. And I have these motion signals here. And I want a smooth step on position. And this is basically a trajectory for what ultimately will be an actuator, which will, the trajectory that I'm going to choose right now is that starting at 1 second and over a 5-second period, I want to transition or basically move that mass, that orange ball, from a position 0, which is my initial position, to a final position of 0.5. All right, and the SI units are implied, therefore that'll be 0.5 meters. All right. And I think we got it. Let's go ahead and give it a shot. And again, we want the blue curve on top of the yellow curve here. All right, which looks good. And I think I'll wrap up the video with two more things. All right, so I want to take this and I want to get that trajectory right off there. All right, that fit in pretty good. Now this is a 3-component signal. We only want the first component. There's a good block called the selector block. All right, there it is. And we want to pick off the first signal. We just slide it on right there. And then the other thing I want to do is I want to measure force. And so now it's orange, and that basically means 3 signals are now stacked. That's the orange one, that's the blue one, and that's the yellow one right there. And so orange ends up on top. And there is really kind of the whole point, which is that's the force required to move it from 0 to 0.5, starting the transition at 1 second and finishing it at 6 seconds. And notice it ends up at a value of 50, and that's essentially the force of the spring being stretched 0.5 meters. Thanks for watching.